When you guys watch the video, you should let me know if the glare here is actually a problem. Okay, let's begin. So we are going to start linear algebra today, I promise, but I still want to give you a little bit more motivation before we jump into things, because for a while we're going to be talking about just a lot of definitions and getting to know our way around things, and you can kind of get into the rut of what's the point. So I thought I'd talk a little bit more about why it's important to study the things we're studying and what you should really be taking away from the context. In fact, in the first lecture I said linear algebra is, we're really studying vector spaces, which are just sets that have special properties, and linear transformations on vector spaces, which are just functions between these sets. And you might think of why that would be worth it. I mean, of all the sets that we could possibly study, we're going to study this one set that has these arbitrary 10 things that work. And of all the possible functions that we could study, we're just going to study one kind of function that has two properties. Like, what's the point? Why would we even study a function in the first place? And we're often, especially in calculus, we're kind of trained to look at functions as looking at having certain properties themselves. So we can look at a function and say, oh, this function is differentiable, or this function does this, or this function is continuous, or blah, blah, blah. But it turns out that functions can actually tell us a lot of information about the sets of things that they act on as well. And so by knowing about a function, we can automatically know about the sets that those functions operate on. So, and I can give you an example, which is not directly a linear algebra example, but it might, if you haven't thought about this before, it might open your mind as to the possibilities that we can get by looking at functions and what it tells us about the sets that they operate on. So, for example, let's look at counting. When you're looking at counting, okay, when you write down a number for something, what are you actually saying? What is the reason for having a number or a list of things that you want to count? Right? What would be one of the most basic motivations in doing that?
Keeping track of amounts. Keeping
track of amounts. Like if I write down, oh, there are 4 of this thing and there are 2 of those things, what would I be able to say?
Twice as many units of one as the other.
Right, and that's more, right? You'd be able to say, okay, a group of 4 things is bigger than a group of 2 things. You want to keep track of things and their relative sizes. But here's something that we can claim, right? This is the set of integers. I believe I gave you that symbol before. And this is the set for real numbers. I believe I also gave you that symbol before. If I put the magnitude symbols around these sets, this is talking about the number of things in them. And it turns out we actually know that that is true. Right? Now, if you think about that claim, there's an infinite number of things here, right? There's also an infinite number of things here. Describing them by a number in our number system is not useful in any sense. But at the same time, how do you know that there are more of this than that if they're both infinite, right? Saying that there are more real numbers than integers, that's kind of a weird thing to claim to know, right? How would you know? Show me the guy who sat down and counted all the integers. Show me his ledger. Where did he write down every single possible integer? Where did he write down? Can you even write down every single possible real number? Let's say you start to write a list of real numbers. Okay, what's your first real number? 0. Okay, what's the second one? 0.0000001. Okay, what's the third number? Oh, but wait, there's the number in between those. I could have put more zeros than a 1. Oh, there's a number in between that. I could have put one. You would never be able to get anywhere in this list. Once you write down 2 real numbers, there's an infinite number of real numbers in between them, right? How are you going to even write down a list? What kind of magical ledger was this guy using? How can you claim to know something like that? Numbers don't apply. How can you say there's more of one than the other? And the answer is functions. Functions is how you know. I can talk about these sets because I can talk about functions between these sets. And I'll illustrate how you can know something like this with a finite example that you can see. For example, without actually counting them and writing down all the numbers and keeping track of everything, I can know that there are more desks in this classroom than there are students, right? No, I could count you, but I didn't. I don't have to, right? How would I know that there are more desks than there are students?
You see us?
I can see you, right, but what if, what if there is something else that we can't see all the real numbers? Tell me a way, how would you keep track of everything?
There's no student. The desks are empty. Some of them are
I can
empty.
find a desk that's empty. In other words, if we want to be very abstract and think of things very elementary, we can think of the student sitting in the classroom as a function, right? Follow me here, stay with me, okay? Let's say I separate the two sets of things. Students, desks in the classroom. The students are my domain, right? The desks in the classroom are the codomain. A student sitting in a desk is me assigning a domain element to that codomain element, right? There's one student in every chair, right? Which means this is a one-to-one function. Students sitting in a classroom is a one-to-one function. The fact that there are missing chairs, there are chairs that have no students in them, what can I say about the function itself? It's not onto, right? Because onto means every element in the codomain was assigned an element from the domain, right? So the fact that I can create a one-to-one function that is not onto, in the finite case, that's enough for me to say, you know what? There are more things in the codomain than there are in the domain. And I didn't have to count things, I didn't have to list things. I could just say, I created this function, and by looking at that function, I can talk about the two sets of things, right? What if I had a lot more people, right? I'm just, okay, everyone took a seat, and there were more people. And they're like, okay, you know what, everyone, I don't care, everyone to a desk, get on a desk, people are sitting in each other's laps, they're on the desk, and blah, 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 right? So that I made the function onto, all the desks are filled, but now they have several students on each desk. Now the function is no longer one-to-one, but it is onto, right? Now what can that tell me about the sets? There are more students than there are chairs. The fact that I've made an onto function that is not one-to-one tells me that there are more elements in my domain set than there are in my range set, okay? Now what if we're in the scenario where every desk has a student sitting in it, there are no more students to seat, that's a one-to-one and onto function. And just by looking and notice that every desk is assigned a student, there are no desks that we're not assigning a student, and every desk has exactly one student, I can make a conclusion from that, there are the same number of desks as students, right? So I can actually make a conclusion about the number of things there are without actually counting. And what gave me the power to do that is a bijective function. Right? So, yeah, there's an infinite number of things, and I didn't have to count them, and I can't count them. Like, a supercomputer would never be able to count these things. But I can know this, right? Because of functions is how I would know. Here's another thing that's pretty cool about functions. If I give the function a certain property, I can tell whether the sets that the function operates on share that property. Okay? Let's look at, for example, linear transformation. We're going to talk about those. Right, so let's say here I'm in R and I'm mapping to R. I'm using a linear transformation. I'm thinking of the function f of x equals 2x, but that's not the main focus. I just want to emphasize something here. If I pick the number 1 here, what does that map to?
It's double.
Right, so what does it map to? 2. It goes to 2. Okay. If I pick the number 3 here, what does that map to? 6 under this function. Now let's say I combine these two in here. If I add them, what do I get? Right, so I did an addition operation and I add them.
4.
I would get 4. Now what does that map to over here?
8.
Maps to 8 under this function. Now what I want you to notice is that if I ignore this for a second and focus on this, if I do the addition operation on these two, what did I get? I got that same guy, right? So notice this is basically me saying, that f of x plus y is equal to f of x plus f of y. Right? In other words, I've created a function that has this property. So corresponding guys that have a certain behavior in one set, they will correspond exactly to guys that will behave exactly the same way in the other set. I added these two, I get that one. The corresponding guys of these are over there, and if I add those two, I get the corresponding one of the guy here. They all correspond, they'll behave the same, right? Corresponding people have the same behavior in terms of this operation. So by forcing my function to have a certain operation or quality or behavior that I care about, if I can slap that function on top of two sets, and it turns out that that function actually works, I can connect these in the sense that I maintain a function, it can tell me about how the elements in each set themselves interact with each other. In other words, if this was a set I didn't even really recognize because it just looked weird, it was an alien language, and this is blah blah blah, and this is da da, right? So I can know everything about this set. These are just numbers. We're familiar with numbers. We've been counting since we were able to walk, or maybe even before, right? But now, in math research, we're trying to solve this new problem that comes up, and I encounter this other set of things here, and I don't really know anything about that set of things, right? But for some reason, something reminds me about numbers. So what I can do is, I can have a function that has a certain property, connect all my numbers to that thing, and if I notice that everything corresponds, then it turns out that if I can solve a problem here, I can automatically solve it there, right? Because everyone will correspond. They behave the same way, even though I might not recognize them as the same thing, right? So the fact that I have a function that describes a certain property in terms of, in this one, preserves the addition property, it means that in terms of adding things, if I know how this guys over here behave, I will automatically know how guys over there behave. So it's kind of like the function is some sort of witness protection program, right? Where you have John Smith over here, goes through the program, and he becomes, I don't know, Kevin Little, right? But the thing is, if you know about all the traits of John Smith, you automatically know about all the traits of Kevin Little, right? It's really the same person. You just change his name on paper to protect his identity, right? But behaviors over here translate to behaviors over there. So the thing is, we can study a set and know everything about that set. And by virtue of the fact that I can connect that set with another set with a function that has a certain property, and that property is preserved, it turns out that everything I know about this, I will automatically know about that, right? So I can substitute things, and my ideas and constructs and theorems and everything I know about over here will apply to this new arena, right? Which is a very elementary concept in math in the first place, right? Like, how did math build on each other? You learn to solve simple problems, and then you build on that and learn to solve more complicated or uncomplicated, and you build on it. And this is, a function ends up having that essence built into it, right? So functions can tell me about this, how sets are structured. I can know about if they have the same number of things in each of them, and if they share the same behaviors, exactly, right? And the function that is bijective, that preserves a behavior, that such a function is called an isomorphism, right? And if it preserves the behaviors of a linear transformation, right, meaning it preserves those two properties, so that f of kx is actually equal to k f of x, right? Such an isomorphism is called a vector space isomorphism, right? And that can tell me, so if I know something is a vector space, and I can take a linear transformation and connect that to another set of things, which I don't know anything about, but it turns out that the function has these two properties and it's one-to-one and onto, I can automatically know this thing that I'm not sure what it was, it's a vector space. In fact, it's a vector space that behaves just like the vector space that I know everything about, right? And so functions are very useful in that regard. And so last time I kind of showed you how we can use matrices to represent these functions, right? So we can have a matrix A with some number of elements in it, A, B, C, D, E, F, and we can actually think of this as some function, right? That goes from where the number of columns tells you the dimensions of the domain, and the number of rows tell you the dimension of the codomain. So this can be like a function from R3 to R2, for example. Right? So this box, this rectangular array of numbers, represents some function. Knowing about that function and studying this function can tell me about the sets that that function operates on. And so when I know everything about one set of things, like for example in Calc 3, we know pretty much everything there is to know about R3 and R2. So anything that can behave in a similar way, we'll automatically know about them. If calculus can work over here, well, calculus is a bit of a stretch. We need limits. But if the property that the function preserves can work over here, we can do the thing over here. And that's very important to know. So that's kind of where we're going. So we're going to take a while, and we're going to be studying these guys. But I want you to understand, what we're really doing is studying the functions that will connect certain types of sets that we care about. And we're studying the functions that have two properties that we want to preserve. And being able to talk about them will ultimately help us to talk about the functions, which will ultimately enable us to talk about the sets that they're operating on. Right? So that's where we're going to kind of end up. We're going to like end the semester here. It's going to come full circle, and we're going to talk about these functions in the most general sense. But until then, we're going to start looking at these guys, the matrices, how they work, the properties that they have, and all sorts of definition and things that go along with them. That's where we're going to start. But there is an end game. You should consider this as you just studying the properties of a function that you will make use of later. So we're finally in lecture 1, where we're going to start chapter 1. I forgot, 1.1. So we're going to look now at matrices and matrix algebra. So what are matrices and how do we do algebra with matrices? Which I've kind of illustrated before, but now we're going to write them down exactly. And hopefully now when I write down the definitions, there is some background where there's going to be some sort of intuition and nothing is going to jump out as too crazy. So here. A matrix is a rectangular array of numbers. Now there are a lot of linear algebra textbooks that start out this way and they don't tell you, okay, you have a rectangular array of numbers, why do I care? Well, because they're functions. We're going to use them later. Right? But they're not usually going to mention that. You usually see a definition in a book that goes something like this. A matrix is just a rectangular array of numbers. So example, 1, 2, 3, 4 is a matrix. Or you can use either notations as this as well. They mean exactly the same thing. It's just, I'll usually write this one because it's easier to write parentheses on a blackboard than it is to do this. That takes like 3 strokes where this is just 1 stroke. Okay? It's important to know that if you use straight bars though, that's something different. This is different. It's not a matrix, this is actually a number. This is the determinant of that. This is going to be this guy or determinant of that guy, which we'll hit that guy in chapter 2. Okay, so don't worry about that for now. But this is our notation for a matrix. So that's a matrix, it's a rectangular array of numbers. Definition. So the numbers in the matrix are called entries or components. I just explained the title. The plural of matrix is matrices. That's where matrices. Starting very basic here. Explain the vocabulary and everything. Just as how we can give functions names, sometimes we want to give matrices names. matrices can be named, usually using uppercase letters. That's usually. Right, so it's a hint that when you write down an uppercase letter in this class, odds are, unless you tell me otherwise, you're defining a matrix or you're talking about a matrix. So once you define that, every point after this in that problem, whenever you write down uppercase A, it can be replaced with this matrix. Horizontal sequence of numbers. Of entries. This we will call a row of the matrix. And the vertical sequence of entries. This we will call a column of the matrix. Rows and columns are numbered. From top to bottom or left to right, respectively. Starting at 1. So for example, if I have the matrix B, this is 1, 2, 3, 4, 5, 6, then I can take this is row 1. This is row 2. Whereas if I look at the vertical entries, the vertical sequence of numbers, this here will be column 1. This here is column 2. This here is column 3. So a matrix is a rectangular array of numbers. These numbers are called entries. Horizontal sequence of numbers is a row. Vertical sequence of numbers is a column. The entry in the ith row and jth column is the ijth entry. And it's denoted by a subscripted lowercase letter. In the following way. So I can say A is a matrix. Let me again use 1, 2, 3, 4. I can start to talk about individual entries in this guy based on the row and column that they appear in. Let me extend this a little bit. Right? So I can look at this number here. Notice that it's in row 1, column 1. So I can use a lowercase letter because that's uppercase A. I can put 1, 1. That will be the number 1. Or I can say, talk about the 5 here. Notice that that's in row 2, column 2. That's A2, 2 is 5. Or I can talk about the 6. That's in row 2, column 3. So that would be A2, 3 is equal to 6. Right? So i.e., when you look at Aij, I is the number of rows, it's the row number. You say row first, J is the column number. Another thing we want to know about is the size of a matrix. we can talk about an m by n matrix if it has n rows and n columns. Right. So, example, A equals 1, 2, 3, 4, 5, 6 is a 2 by 3 matrix. Right? So that's how we define the size. And notice we always put the number that represents the row first, number that represents the column second. Every now and then it'll be convenient to write down matrices using this notation. So I can say A is the matrix Aij, and I might put the subscript n by n. So that's when you want to actually define a matrix based on some formula that has to do with the entries. So you can denote, I will have a formula in terms of I and j that describes the ijth entry, and you put a little subscript here to denote the size of the matrix. Right, and I'll give you some definitions later where I'll actually write it like that because it's easier to write it out that way. This is mostly something I'll do on the blackboard. Textbooks probably you won't see it so much, but I might emphasize sometimes when I'm writing a matrix the size of the matrix I'm talking about. Sorry, uppercase A and lowercase this to mean an m by n matrix called A. So that was just introducing a bunch of notations. Let's talk about vectors. A 1 by n matrix, we call that in quotations, right? This means it has one row and possibly n columns. This is called a column matrix, a column vector. That's just a reuse of the word. The word vector we'll be interpreting in a much more general sense pretty soon, by the time we hit chapter 4.
Is that an I by n matrix?
1, the number 1.
A
So
1 times n matrix? Oh, I see. Okay.
Oh, row vector. And if it's an m by 1, so if there's one column, it's called a column vector. So you might see that phraseology used, but we would in general interpret vector in a much more general sense than that. Here's an important fact. So we're going to define the equality of matrices. How can I say two matrices are equal? And we write A equals B if A, B have the same size and corresponding entries are the same. That defines equality. And so every now and then you might have a matrix equation that you need to solve. So if you had something like 1, 2, 3, 4, we'll talk about this later, and you had here like x, 2, 3, y plus 1, then that would mean for this to hold, if you're assuming these are equal, it means that the corresponding entries must be equal. So it means that x must be 1 and y must be 3. Because equality of matrices mean they have to be the same size and corresponding components have to match up. They have to be the same. Now we're going to do a little algebra. So here's how we will add two matrices. First note, let A m by n and B m by n be matrices. Note, same size. So there are times when I'll actually write that, but I might not always shout at you, oh, that means they're the same size. You have to pay attention to subscripts whenever they arrive. And I won't use the same letters unless I'm really referring to them as the same thing or the same size. So these are both m by n matrices, so we can be the same size. We define A plus or minus B to be it will be Aij plus Bij. And it will also be an m by n. In other words, you add the corresponding entries, and that is captured into this formula written in the previous notation. i.e., add or subtract corresponding entries. And why? That's how it worked out when we thought of these guys as functions. The x's, we had to combine like terms, right? That translates into adding corresponding entries. Example. Do A plus B here because they're of the same size, and so what I can do is I can add the corresponding entries. And the result of that will be 1, 3, 2, 6. Or I can say take B minus A, and that's me subtracting the corresponding entries. That's 0 minus 1, 1 minus 2, minus 1 minus 3, and 2 minus 4. That would be minus 1, minus 1, minus 4, minus 2. And if I were to ask something like A plus C in that case, that would be undefined. They're not the same size. And that makes sense because it means that I'm trying to combine things that have different dimensions, and one of them has too much information, one of them has not enough information. We can't actually reconcile the information. So that's how you add and subtract matrices. It turns to be very intuitive. As long as they're the same side, add or subtract corresponding entries. We can also talk about scalar multiplication of matrices. k be a scalar, and a n by n equal aij n by n be a matrix, then the scalar multiple of a, ka, is defined to be the matrix in which each entry is multiplied by the scalar. Sort of how we do with vectors. You multiply by a scalar, you just multiply every component by that scalar. Example, a is equal to 1, 2, 0, 1. Then that means if I take minus 2a, that will be minus 2, minus 4, 0, minus 2. So that's a scalar, this is a number. In this class, unless otherwise stated, the scalars are always going to be real numbers, but there are contexts in which they're not. They just have to belong to a field, which is again another generalization of the real numbers. Here's a weird thing, but it's just me defining a particular name. So don't think of this as a general thing. But there's the idea of a zero matrix. A is called a zero matrix. If all its entries are zero. Denoted by 0 with a vector on top of it, or 0 and by n if I want to emphasize the size of a matrix. So I can have a 1 by 1 zero matrix, or I can have a 2 by 3 zero matrix, or I can have a 2 by 2 zero matrix, or I could have a row vector that's a matrix and it's a zero matrix, etc. That's called a zero matrix. Right? Any matrix where all the entries are zero called a zero matrix. In general, this symbol means something else. It doesn't have to literally be involving the number 0. That's why I said it's kind of a weird definition, but think of this as a proper name. It's the name of the thing. Here's an aside. Suppose I define something that I call addition, and this is how it's defined. Who would your zero matrix be?
1, 1, 1, 1.
No.
It wouldn't? Alright.
Right? Remember I gave you that list of things that make a vector space, and one of them had the definition of zero. Definition of zero was whenever you add two things, you get back the original element. Turns out if I have A, B, C, D, and I want to add something according to this rule, to make sure I get back A, B, C, D, this has to be -1, -1, -1, -1, so it kills all the plus ones. Right? So 0 doesn't mean involving the real number 0 all the time. You have to be aware of that. In the case of matrices, though, it will involve 0, because when we do addition in terms of matrices, the plus sign is the usual plus sign. Pretty soon, we will be redefining what plus means, what times means, and it will depend on context. So you have to be aware that 0 depends on context, right? It's just that in the case of matrices, unless the standard context is just all entries 0, but that's coincidence. Let's talk about matrix multiplication.
Yeah.
Multiplication. So that's A m by n and B n by p. Alright, so here pay attention. Notice that here this is an n by n, this is an n by p, which I'm telling you that these two have to be the same, but these two are allowed to be different. Right? So the number of columns in the first one must be the number of rows in the second. It's very important that they actually line up that way. Then AB is defined to be Cij, and that will be an M by P matrix. Such that Cij is the dot product of the ith row A with the jth column of B. Okay, now you see that definition, you're like, what? Why? Addition and subtraction seem to be very intuitive. Then you get to multiplication, it has this weird definition. First of all, it doesn't always work. Things have to line up a certain way. Second of all, it's defined in terms of some sort of dot product of rows and columns, which wouldn't make sense to you at first glance, but because we know they're functions. And when we say product, we really mean composition. This will make sense. So i.e., so if we have A times B, what you need to know is if this is an M by N, that is an N by P. Turns out that these two must be the same to multiply. The outer two, this gives the size of the result. Right? So that would be some other matrix C, which is going to be an M by P, where the entries of C are defined in precisely this way. And the reason why is because it's a model for composition of linear transformations. And that's how it works out when you do combining like terms and all that stuff. Okay. So let's do some examples. So I'm defining these three matrices. Notice that here, this is a 2 by 3. This is a 3 by 2. This is a 2 by 2. Here's what we're going to do. We're going to find AB. We're going to find BA. We're going to find CA. Look at AB. This guy here is a 2 by 3. This guy here is a 3 by 2. So immediately these guys match up, which means that yes, we can multiply, right? That's the first thing you have to check in terms of the sizes. You also know what the result should be. Result is a 2 by 2. Okay, so let's actually do that. Okay, so now let's look at how these guys are set up. So I know that the result should be a 2 by 2. In fact, I can kind of look at this as C11, C12, C21, C22. Right? Those would be the entries. So I automatically know the form that the result is going to take. Now, by definition, the Cij entry is the dot product of the ith row of A with the j column of B. So the guy that I'm going to put here is going to be the first row of A dot producted with this first column of B. Right? So I'm going to take this first row, I'm going to turn it sideways and dot product with that. So I'm going to multiply corresponding entries and add them together. And I'm going to replace that. So this is going to be 1 times 1 plus 2 times 0 plus 3 times 1. And that will go in the first row, first column. Similarly, here was C12, which means I should take the first row here and the second column there. So I'm going to take this, dot product with that. That's going to be 1 times 1 plus 2 times 1 plus 3 times 2. And that's going to end. We're going to continue here. So here we're going to do 3 times 1 plus 4 times 0 plus 0 times 1. That's going to go there. This position was the C22 position, so it's the second row, second column. It's going to be 3 times 1 plus 4 times 1 plus 0 times 2. So that would be a 2 by 2. this means the matrix AB is going to be 1 plus 0 plus 3. It's going to be 4. 1 plus 2 plus 6. That's 9. 3 plus 0 plus 0. It's 3. And 3 plus 4 plus 0. 7. And if you think of this as a function and that as a function, this is just the composition of functions. That applies this rule first, then that would be second. And that would be the multiplication. Another way you can look at it is that the row of the result is determined by the rows of the first matrix. So the first row times the columns will create the entire first row of the result. So first row, first column here. First row, second column here. You have a third column, first row, third column here. First row, fourth column here. You'll stay in a row until all columns are exhausted. Then you move down to the next row. So second row, first column here. Second row, second column here. And you can keep going. Every time you swap a row, every time you move down a row here, you'll move down a row into your result. Another thing that you want to be able to do is that for this class, a lot of things we're going to be doing by hand that otherwise you'd use a computer to do. But it's just to make sure that you guys understand what's going on in the background. You really want to start writing things out in such a way that it's very strategic, or it's following some sort of pattern that you can always check on, because you're going to make arithmetic mistakes, so you need to be able to track them very well. So notice how I wrote this. The numbers in the parentheses are the same numbers in the parentheses, right? I kept the guys over here in parentheses, and the guys over here, I kept them outside of the parentheses to the side, right? It's not because I have to do that. I just want to create a pattern so that if I go somewhere over here and I'm working with something, I realize, oh, something's off, like I missed an answer, the answer is wrong somehow, I can go back and I can definitely look who is out of place, right? I'd be able to see. So one thing I'd recommend is try to be pedantic in the way you write things down, so that you have a certain pattern of how you always write things, and you can tell when the pattern is off if you ever have to recheck your work, because it's going to get kind of hairy with all the numbers you're adding in. Right, so while you're not doing anything complicated, doing it a bunch of times over and over and over, you might have a lapse in concentration. So you want to keep things very streamlined to be able to see them. That being said, are there any questions about this or about how I did it or what happened? Okay, let's do the other one. EA. Okay, you guys tell me how to do this one. Is that defined, first of all?
Yeah.
How do you know?
Inside.
It's a 3 by 2, and this is a 2 by 3. These are the same. So yes, it's defined, right? So I know that it's defined here. Okay. What should be the size of the answer? Right. Answer should be 3 by 3. So it is defined, and I know what I should be getting at the end of the day. Okay, so let's actually get this done. 1, 1, 0, 1, 1, 2, 1, 2, 3, 3, 4, 0. All right, go. What's the guy here?
So 1 times 1 plus 1 times 3.
Here?
1 times 2 plus 1 times 2. 1 times 3 plus 1 times 4.
Oh, I need more space. What's next?
That's it. You gotta go to the next row.
Right, you go to the next line. You're done. I was trying to see oh yeah, it's going to be this. No, you stop here. You've gotten to the last column. So you use the first row, and you literally multiplied each column. So the first column here, the second column here, third column here. You've exhausted all columns. Move to the next row at that point. You know that's where you stop. So the first row we took care of. Now we're going to focus on the second row. So this becomes
0 times 1 plus 1 times 3. 0 times 2 plus 1 times 4. 0 times 3 plus 1 times 0.
Okay, I've exhausted a column, move down to the next row because there's a third row. So I already did the first and second row, so I'm going to move down. Here it's going to be
1 times 1 plus 2 times 3. 1 times 2 plus 2 times 4. 1 times 3 plus 2 times 0.
Notice how we line them up. 1 is always in the parentheses here, 3 is always in the parentheses here, 2 is here, 4 is here, 3 is here, 0 is here. And then the numbers over here are always going to be the same. So it's 1 and 1, 1 and 1, 1 and 1. Here it's 0 and 1, 0 and 1, 0 and 1. So it's 1 and 2, 1 and 2, 1 and 2. So you kind of want to think like a computer, how a computer would do things exactly. We'll just follow a program and it always does things the same way. You want to kind of model that. Because computers are great at doing this sort of thing. So yeah, so that ends up being a 3 by 3, which we can simplify. I think we have enough space here. So now you just simplify. So that's 1 plus 3 is 4. And 2 plus 4, it's 6. 3, 3, 4, 0. And that's 6 plus 1, 7. 8 plus 2, 10. And 3. And so that would be the product of those two. Notice it is a 3 by 3. Right? So the sizes seem to work well. If for some reason you have the feeling that one of these numbers are off, go back and check here where you really line things out so you can tell if something is off. Questions about that? Yeah?
Does that mean you can't multiply two matrices that are the same size?
Come again?
Like two matrices that are the same size, you can't multiply them, right? Like it's 2 by 3 and 2 by 3.
It depends if they're square, if the rows and columns are the same. So if I did like a 2 by 2 and a 2 by 2, those can multiply.
Oh, right.
Right? If I do a 2 by 3 and a 2 by 3, then no.
Yeah.
Right, so it depends. You really have to pay attention to the inner numbers versus the outer numbers. That's where you want to focus on. Not necessarily the size in general, but how the inner numbers and outer numbers kind of line up.
So you can't do A dot B?
You can, but we usually don't write it.
Okay.
Right, because multiplication here really means composition, which we discussed in the first lecture. Here's another thing that should jump out at you. Is there something that jumped out at you? AB, BA.
They don't commute?
They don't commute. I multiplied two matrices in a different order, and I got, not only did I get different numbers, I got different sizes. The dimensions are even completely different, right? AB is a 2 by 2, and BA is a 3 by 3, so there's no hope of them being the same. So you should also realize that matrix multiplication is not commutative. That was BA. Let's look at CA, just to get a little bit more practice here. So C is 1, 1, 0 minus 1. A is 1, 2, 3, 3, 4, 0. Can we multiply those?
Yeah.
Right, this is a 2 by 2, this is a 2 by 3. 2's are matching up, and we know the result should be a 2 by 3. So let's actually jump into it. So quickly, what would this be?
1 times 1 plus
1 times 3. Then I would have 1 times 2 plus 1 times 4. Then I would have 1 times 3 plus 1 times 0. Then I would have 0 times 1 plus minus 1 times 3. I would have 0 times 2 plus minus 1 times 4. And I would have 0 times 3 plus minus 1 times 0. So that's a 4, 6, 3. And this would be a minus 3, minus 4.
Is there a small error on the corner? The minus one?
No, I think that's fine. It's 0 times 3 minus 1 times 0.
No, above that.
Above this would be
Oh, no,
the
no, yeah,
first
yeah.
row, sorry, column, so it's 1
Okay.
times 3, 1 times 0.
Sorry.
It's fine. What about A times C, AC?
No. Yes. It's undefined.
Undefined.
This here's a 2 by 3. This here is a 2 by 2. These guys do not match up, so this is undefined. Which tells you how extreme that non-commutativity applies, right? Not only can you get different answers, but it's possible that you can get an answer one way and not even be able to get an answer the other way, right? So commutativity really does not work with matrix multiplication. By the way, there are times when I see students in the class doing proofs where they swap matrices in the proof, and I'm like, not paying attention, you can't do that. So things like these are going to be important. So understand how matrix multiplication works, when it can give us an answer, when it can't give us an answer, and notice that the order matters. So I should probably mention that now. So note, order matters here. So by the way, this also can show up not just if you're writing A and B, but it also can show up in terms of solving equations. So if you have A equals C or something like that, and you want to multiply both sides of that equation, this matrix equation by matrices, if you do this, you're wrong, right? So you have to be very careful here. Why? Well, B is multiplying on the right here. It's multiplying on the left there. It's a completely different thing. At least you have to assume it is, right? You have to do it that way. And so little nuances like these are going to be important. You're really going to have to pay attention to your definitions. So it'll show up when you're solving equations, or if you just have a product of matrices. You need to know you can't just write whatever order you want. Right? You have to be in a context where you know the matrix multiplication commute, and there are very few contexts in which that will happen. So order matters, it's not commutative, so that has to do with when you're writing down a product or solving equations. If you're multiplying on both sides of a matrix equation, you need to multiply on the same side of both sides of the matrix equation, or you end up with something incorrect, usually. And pay attention to sizes. So those little subscripts, they're very important. Right? So that's why I took the time of writing them out, so you know you should be paying attention to this. You know when multiplication is defined, and what the size of the result should be. So don't overlook these small nuances. They're the things that are going to get you. want to fall into a comfortable habit too much here, because we're generalizing things a lot. Okay, what else do I need to define? Square matrices. So that was matrix multiplication in a nutshell. Hopefully you guys understood that. We'll have homework problems where you get a lot more practice on those. So a lot of times I'll just use the subscript n by n so you can understand that I'm talking about square matrices. These are important. There are a lot of theorems in linear algebra that will only work for square matrices. It's a very important kind of thing. One way you can think about this is that because the rows is the dimensions of the output space and the columns is the dimensions of the input space, this is sort of talking about a function whose the dimension of the outputs and the inputs are the same, which in other words is telling you this is the only kinds of functions that will possibly have an inverse. No other kinds of functions will have an inverse. So for you to even consider something like finding the inverse of a matrix, you can only actually do that for square matrices. And there are a lot of theorems that only apply to square matrices, so knowing when you have a square matrix, you should be able to recognize it. Just means the same number of rows and columns has a lot of implications. So this is called a square matrix. So it could be a 2 by 2, a 3 by 3. So you can have this guy, are squared. You have a 2 by 3, not squared. Right, because this is a 1 by 1, that's a 2 by 2, this guy's a 4 by 4. Right, same number of rows and columns, that defines a square. This here is a 2 by 3, not square. Yes?
Does that mean the square matrices are commutative, or does that apply
No,
to just all matrices?
no, square matrices are not commutative in general. Yeah, it's a lot harder to say commutativity than that. So they're not necessarily commutative. Square is just referring to the size and nothing else. But knowing the size is important because there are certain properties you may or may not assume it has. So if I have a matrix like this, I wouldn't even think about looking for an inverse or a determinant because it's not square. Whereas if I have guys like these, I may want to search for an inverse or to find the determinant in certain contexts. Here's another definition. A diagonal matrix I probably need to define the diagonal for you. The diagonal, often referred to as, sometimes they refer to it as the diagonal, but the full name is really the main diagonal. Of a square matrix. I mean, you don't talk about diagonals of non-square matrices. So you can have this huge matrix, so like A11, A12, all the way down to A1n, A2n, 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 all the way down to AN1, AN2, all the way down to ANN. If you look at this sequence of numbers here, that is called the diagonal of the matrix, or the main diagonal of the matrix. Definition. Trace of a square matrix is the sum of its diagonal entries. There are many formulas that depends on the trace, and so knowing what that is can be useful. So, example, if A is the matrix Aij n by n, then here's the notation TRA, this is the trace of it. Is just going to be A11 plus A22 plus ANN. Add all those guys up, get a number, that's called the trace of the matrix. Diagonal matrix. And there are going to be many things that only work on diagonal matrices, and diagonal matrices are going to be nice for algebraic reasons. So those are going to be kind of like your functions that have a certain kind of symmetry that you can take advantage of. And so a lot of calculations will work out very nice with diagonal matrices. Sometimes you define this in terms of the affirmative or the negative, but whose non-zero entries, if any, are all on the main diagonal. Example. Right? These are all diagonal matrices. If you look at their main diagonals, if any non-zero number occurs, they will be on that diagonal. But of course, it doesn't have to be non-zero. But the important thing is, literally everywhere else there are only zeros. If I have a zero in here, it's not a problem. But any non-zero number that occurs have to occur on this main diagonal. Such a matrix is called a diagonal matrix. Sometimes we might do shorthand here. So I might write a matrix where I might list things on the main diagonal, so I might use A11, A22, ANN, or asterisk or something like that, and I'd write a big zero here and a big zero there, and it should be understood that I'm talking about a diagonal matrix. something called the identity matrix. Super important matrix. You can think of this as the one for the matrices, or the identity function for the matrices. So this is a square matrix. This is a square diagonal matrix. It's definitely always diagonal, which is implied. If it's diagonal, it's all automatically squared. So the identity matrix is the matrix where all its diagonal entries are 1. Specifically, the number 1. Example. 1. Etc. This could be all zeros here, it doesn't matter. The n by n identity matrix is denoted big I with a subscript n. We may write I if understood, if the dimensions are understood. But you might want to emphasize what dimension you're working with. You write I in. So for example, this guy is I1, this guy is I2, this guy is I3, this guy is IN. Super important to matrices. So the identity matrices are as important to matrices as the number 1 is important to a number system. It's a very important, forms a very important property, and we'll look at a lot of cases where this guy actually shows up. But the main property here is that it is the multiplicative identity. In other words, it's that guy that if you multiply it by a matrix, you will get the matrix back. Kind of like how 1 is the multiplicative identity for the real numbers. So 1 times x is x, right? Or x times 1 is x. Any guy that when you multiply by something according to your rules of multiplication, you just get the guy back. You get the identity of the guy you multiplied. That's called the multiplicative identity element. And this is the multiplicative identity element for the matrices. So i.e., if A is an n by n matrix, then if I take I times A, I will get A. And if I take A times I will get A. What is the size of the matrix here?
M. M.
It's the M, and this is an IN. Right? So again, because of order, right? Because this is an M by N, right? So in order to multiply, the inner numbers have to be the same. Right? This is an M by N. So in order to multiply, the inner numbers have to be the same. Okay? So who you use as the identity can matter in what order you're multiplying in. That should always be a concern. Multiplication should always have any order, always have order as being a major concern. But once you get the dimensions right, multiplying will give you the matrix itself back. Because basically the 1 just multiplies and give you back the current entry, and the rest of the zeros in the row eliminates all non-corresponding entries. So we can do something like, we can go back to our A, 1, 2, 3, I believe it's 3. It doesn't matter if it's not the same example. So the thing is, if I take I2 times A, right, that would be 1, 0, 0, 1. This would give us 1 times 1 plus 0 times 3, 1 times 2 plus 0 times 0. 1 times 3 plus 0 times 4. Move down to the second row. 0 times 1 plus 1 times 3. 0 times 2 plus 1 times 0. 0 times 3 plus 1 times 4. So now the 0 is going to kill that. That's a 1. That's a 2. That's a 3. This is a 3. This is a 0. This is a 4. That's how you got back 8. Right? And that will always happen. As long as you can, as long as the size is the right one to be able to multiply, you will always get back the matrix when you multiply by the identity. That's why it's called the identity matrix. It's a very important kind of diagonal matrix. And diagonal matrices are square matrices where they have zeros except from possibly on their main diagonal. So this entire section is just a bunch of definitions. We'll be using it pretty soon. So how about transpose of a matrix? A m by n in the matrix. Its transpose which we will denote A with the subscript T. Is the n by m matrix. Notice that the order is switched. Defined by A transpose would just be, so if A is equal to Aij m by n, then your A transpose would be Aji. N by n. Basically what that does is it switches rows and columns. So the first row becomes the first column, the second row becomes the second column, etc. So example, if A is 1, 2, 3, 3, 0, 4, then if I take its transpose, that's 1, 2, 3. First row becomes your first column. 3, 0, 4, and the second row becomes the second column. You interchange rows and columns. And that's called a transpose. I'll more, like, if I'm saying it, I'll mostly say this. Oh, A transpose, and you know what I'm talking about. But these are very important symbols, as well as I. Like, there were times in my previous classes where in my question I put I, blah, 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 and students assumed it was the inverse. No, I will always mean the identity. Right? It's a taken letter. Like, I would never name another matrix I. I will always refer to the identity matrix. Similarly, A to the T will always refer to transpose. It's a very notational thing. It always refers to the transpose. And I always refers to the identity matrix. What other definition do we need? A1, A2, A3, AN. We'll use this more with vectors later, but just in case it shows up with matrices, I want you to know what's going on. B matrices of the same size, C1 to Cn be scalars. Then the expression C1A1 plus C2A2 plus CNAN is called, do you know what that's called, such an expression? It's called a linear combination. A very important idea. Right, so there will be times where I'll be talking about, oh, this is a linear combination of that and blah, 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 blah. You should know what I mean. It means that if I add them all together and multiply by constants, I'm talking about expressions of this form. So an expression like this is called a linear combination, and there will be a multitude of reasons why we want to construct such an expression. And the value of the expression can tell us a lot of things. Next, I want to tell you about some properties. So this is actually 1.4. I'm just going to mention some algebraic properties of matrices. So we'll actually go back to 1.2 and 1.3, but I think we might as well introduce these now. It's not going to be a major focus, but I just want you guys to know what operations are allowed when we're talking about matrices. So I'll just list them off in no particular order. So A plus 0, this represents the right dimension 0 matrix, equals 0 plus A equals 0. In other words, the 0 matrix is an additive identity. And we're assuming, and again, the pluses mean the sizes are the same. I have A times 0 is equal to 0. Huh?
Maybe it should be A.
Yeah.
0. For
Top
A
one.
plus 0.
A, yes. Right? And if I let, for example, A be an m by n, then this guy would be the n-dimensional 0 matrix, and this guy would have to be an m-dimensional. I'm not going to really worry about that at this point. So this has to do, I mentioned this already, A times I is equal to I times A equals A. other properties that you can know is that addition is commutative, so A plus B is the same as B plus A. So that's something you can assume. Addition is also associative, so A plus B plus C is equal to A plus B plus C. So if you have more than two matrices operating on and you're adding them, you can add any pair that you want in the first place. That also works with multiplication, by the way. So if you have A times BC, it's actually the same as A times B, and then multiplying that result by C. That's another property that you can take. No, AB not equal BA in general. Just for re-emphasis or other properties. We do have distributive properties working. So if I have A times B plus C, this is the same as AB plus AC. Order matters. If I have A plus B times C, this is AC plus BC. So we have distributive laws we'll work on matrices. What else would work? Scalar multiple of a product. So if alpha is a scalar, AB, this is the same as alpha times A times B is the same as A times alpha B, where alpha is a scalar. Transpositions of a product. Turns out if you have a product transpose, this is actually equal to the product of the transposes, but in the opposite order. You have to remember to switch them. We'll talk a little bit more about that later. And inverses have a similar property. What else? Turns out that 1 times A is actually A. That won't always be true, but it's true for matrices. And here I'm talking about the real number 1. There's another property. If C times A equals the 0 matrix, then either C is the 0 real number or A must be the 0 matrix. Again, something we take for granted in the real numbers, but that's actually not something that holds for more general things. And we'll probably actually do an example where I can show you examples where this actually does not work. Where you can't just assume the product of two things equals 0 means one or the other has to be 0. But it works in this case. And we'll actually prove this specifically after we learn about vector spaces. Here's one thing that does not work. The cancellation law, you should be aware, does not hold. i.e., if A times B equals C times B, it does not mean that A equals C. Right? The idea of being able to cancel both sides of an equation doesn't work anymore. So resist the temptation to do that. There's no such thing as cancellation because there's really no such thing as division. It's very hard to get something like that to actually work out. Just in time. we'll stop there for now, and we will start off by talking about. We'll start to use matrices in the next class. We're going to look at systems of equations and all the stuff we can say about them, because it turns out that a lot of problems in linear algebra can be reduced to solving systems of equations. So we'll look at that. So, yeah. This lecture was kind of dry with all the definitions, but I wanted you to know that there's a motive behind all of this. But we need to understand the language and the structure of the things we're doing, what works from what doesn't. I will see you guys tomorrow.
Yep.